Yeah.
Today I'm going to finish our discussion of random vibrations and gust response. And then we're going to talk about flutter. But Stockholm, do you have any questions before we start? I'm not sure I heard that. I don't know. We'll assume they don't have any questions.
I have a question.
Oh, you have a question.
Yeah.
What's your question?
In the piston theory formulation,
Yes.
you have the term that's PW to D.
Yes.
This is alpha, basically, right? This is the.
Well, it would be if it's an airfoil and angle of attack. That's right.
If you want to consider flutter, for example, you need
Yeah.
the second
Right.
degree.
Right.
Okay.
That's right. Okay, let's continue with our discussion of random vibrations and gust response as an example. And let me remind you, I think this was equation 22 from the last lecture, and let me write that down again. This is for one mode whose generalized coordinate is Q1. We arbitrarily but reasonably put in a structural damping term, and then we argued that this linear stiffness term can always be expressed as the generalized mass times the square of the natural frequency times the coordinate. And then we're using piston theory aerodynamics, which simplifies our aerodynamic model. And so it's the density of the flow times the speed of sound. And then for the gust term, it's the gust velocity weighted by the mode shape integrated over the wing or the structure. And then there are also contributions to the aerodynamics from the motion. And those have the following form. Again, it's the same coefficient, but there are actually two terms. There's a term involving the structural velocity, which is in terms of generalized coordinate Q1 dot times the square of the mode shape. One of these mode shape terms comes from the physical velocity, and the other mode shape term comes by the weighting factor that arises from the virtual work. And then there's another term, Q1 times the slope of the mode shape times the mode shape itself, dx dy. Okay, that was the equation. All right. Now, we want to do a couple of things with this. The first thing, if we're going to use random vibration theory and say that the output power spectrum is the square of the transfer function times the input power spectrum, we better find out what the transfer function is. And there are several possibilities for the transfer function. It's really up to us to define what transfer function we find most fascinating. So I know what transfer function I like, but what about you? What transfer function do you like? It has to relate the gust, which is the input, right, to the output, which is the motion of the structure. But what particular aspects of the gust or the output would we like to use in characterizing our transfer function? Shall I make a suggestion? Or do you have a suggestion? No, you're wanting to go on. After a careful thought, and having done this before, I suggest that we do the following. First of all, with respect to the gust, we have the gust velocity. In general, would depend on some point in space on the wing, right? And of course on time. Okay? And we could, I would suggest we do, model that by some function of time times some shape function. This is not a mode shape. This is the shape, the spatial distribution of the gust, right? Someone has to tell us that. And there are standard assumptions in the literature about what that should look like. But for our purposes, we've consulted a gust expert who's told us what this function looks like. Right? But now, because we want a transfer function, we are looking at simple harmonic motion in time. That's the great virtue of looking at transfer function. Simple harmonic motion in time, which simplifies everything in the sense that it's a linear system. The time goes away and it's replaced by a frequency, right? So we're going to assume that this is now WG dot bar bar, an amplitude which doesn't depend on anything, i.e. it doesn't depend on time or space, times E I omega t times this shape function. Okay? There's a lot more that can be said about how you model a gust, but you can read my book or you can consult the literature. For our purposes, it's given. Right? Okay, so with this in mind, we'll call this equation 23. My suggestion is that we have a transfer function which relates the output as characterized by Q1 and the input as characterized by WG dot double bar, which obviously depends on frequency, among other things. Depends on a lot of things, but in particular it depends on frequency. So by definition, this is Q1 bar times WG dot double bar, where we're assuming that Q1 also is some amplitude which doesn't depend on anything, i.e. it doesn't depend on space or time, E I omega t, right? So this is our definition of the transfer function. Of course, this is the usual assumption for sinusoidal motion. So what we're going to do is we're going to take 23 and 25, put it in 22, compute this ratio, and say, that's the transfer function. Yes, Kevin?
In 23 and 25, we use I omega t. Is that the omega, is that the frequency of the gust, or is that the frequency of the thing itself?
It's the frequency of the gust, but for sinusoidal input gust and a linear system, what's the frequency of the motion? It's equal to the gust law after the transient dies out. I mean, we're thinking of steady state here, right? I mean, if you're thinking in physical terms, if I turn on the gust with sinusoidal characteristics in time, there's a transient in terms of the motion of the wing, but eventually if I wait for the transient to die out, I'm in a steady state oscillation where the gust input frequency and the structural motion frequency are the same. Because for a linear system, that's the only thing that can happen. For a nonlinear system, you can have harmonics, you can have twice, superharmonics twice, 3 times, subharmonics 1/2, 1/3. You could even get in chaos. I mean, God knows what could happen in nonlinear systems. But for a linear system, this is the only thing that can happen. So it's the same, really. But I think of it as it's the gust frequency which imposes that frequency on the structure after the transient dies out. Okay? Good question. The answer was fair, but the question was really good. Okay. The answer was accurate, so I'll give it that. Right? Okay, so we're going to take 23. So I could put a sub G on here, but normally you don't. All right? But, okay. The frequency is the frequency is the frequency, to paraphrase. Who said that? Gertrude Stein. Said a rose is a rose is a rose. Or was it Shakespeare? I think it was Gertrude Stein. Anyway. Okay. 23, 25, and 22. Let's see. So H sub Q1 WG dot, the bars up there if you like. It's just ratio, right? I'll write it one more time. And from 22, I can easily see what that is, he said. The numerator is going to be the coefficient from that I get from this term, right? So the numerator is going to be rho infinity, A infinity. I've got this, but this is a ratio, right? So I'm going to cancel out that factor. But then I'll have the integral of the gust shape times the mode shape, dx, dy. All right, see where that comes from? I'm taking this and putting it in here, and because I'm getting a ratio, I'm dividing through by that, so that makes this go away. Okay? And then on the bottom, I don't know if I've left myself enough room. On the bottom, you got everything else. So you've got M1. Yeah, on the bottom I have the coefficient of Q1, right? So it's M1 minus omega squared because I have the second derivative plus 2 zeta 1 omega 1 I omega. This is going to be a complex number, of course, because of the Q dot term plus omega 1 squared and all that. Maybe I should put a bracket here. And then I've got all of these terms, but I'm going to take those on the left-hand side, which is going to change the sign, right? And so I'm going to have plus rho infinity, A infinity. We'll get a Q here, so that's a Q dot. I got an I omega, integral of psi 1 squared dx dy, plus U infinity and that's it. Okay? So I've computed the transfer function. Now, when I square this, I'm really multiplying the transfer function by its complex conjugate, which is going to make that square a real number, even though I have imaginary numbers in the transfer function itself, which is good, because eventually I'm going to compute the mean square, which is a real number. And so if the input power spectrum is a real number, which it is, the gust, I multiply by a real number, the square of the transfer function, I get a real number out for the power spectrum of the output, and then I integrate that over frequency, which in this particular case, you could actually do analytically. Because after all, this is just a polynomial, a quadratic in omega, right? And even when I square it.
This term should not also be divided by the dynamics.
By
By this term.
what do I want to do?
The denominator will be also here. Under this one.
So you want it over here too?
Yeah.
I don't.
Two terms on the right hand side?
No, I'm going to take all these terms, I'm going to take this term and this term, put it on the left hand side, right?
Okay.
You know, that's, but this didn't get multiplied by M1. You okay?
Gotcha.
Thank you. Yeah. Okay, so this, I think this is right, but you can sit down in the quiet of your office and make sure I did the algebra right. Okay, let's interpret this a little bit physically. First of all, this term is the structural damping. It's really mathematically just like that term. So this term from the aerodynamics gives me aerodynamic damping. This gives me structural damping. For most aeroelastic systems, this term dominates, as you could compute it for typical values of zeta 1, omega 1, rho infinity, infinity, and so forth. Typically, the aerodynamic damping overwhelms the structural damping. So even in gust analysis, you often neglect the structural damping. You got to have some damping in the system, because if I excite a system with a random input, which includes input in the frequency range where the resonant frequency exists, if I don't have any damping, the response is going to be infinite, right? So I need to have some damping, but it turns out the structural damping isn't the most important term. What about this term? What does that do? Well, I claim this term, let's look at these terms in terms of their dependence on frequency. This is omega squared. This is an inertia term. In the piston theory, there is no aerodynamic inertia. by the way, in low-speed flow, incompressible flow, there is aerodynamic inertia in the classical model. But in piston theory, there's no aerodynamic inertia. But there is this thing. And this thing doesn't depend on frequency, which means it's like this term. What term is this? This is structural stiffness term, right? Well, this is some people would call this an aerodynamic stiffness term. And depending on the sign, SIGN, plus or minus, it either subtracts from or adds to the structural stiffness. And the sign will be determined by the mode shape. It'll be determined by this integral, right? And rho infinity is positive, A infinity is positive, U infinity is positive, unless I reverse the direction of the flow. But so those are all positive numbers. So it all depends on this sign. And for example, if I took a simple plunge motion, the mode shape would be a constant. I take the derivative of the constant, I get 0. This term doesn't contribute at all. So for plunge motion, there's no aerodynamic stiffness at all. For pitch motion, there is, but if you think about it, it depends on whether you're pitching about the leading edge or the trailing edge, right? Because one way you'll be pitching up, the other way, right? And that would change the sign of that term. Okay. And you can figure out which one would be better in terms of either adding to or subtracting from the stiffness. Okay. Now, this is all I'm going to do for this case, for Gus. This is the whole story. But I will now transition to flutter using the same model, unless there are questions. Anything else you want to know about Gus before we start talking about flutter? No. How about you, Stockholm? Anything else you want to know about Gus before we start talking about flutter?
Yeah, okay.
Okay. So let's talk about flutter. Within the framework of linear theory, and when you get into nonlinear theory, it becomes much more interesting and complex. But we're talking about linear theory. There are only two ways this system can go unstable. One way is the aerodynamic damping could be negative. Within the framework of piston theory, it isn't, right? This is positive, square the mode shape integrated over whatever is positive. It's piston theory always produces positive aerodynamic damping. Typically, in low speed flow, Mach numbers well below 1, the aerodynamic damping is also positive. But once you get into the transonic regime, the low supersonic regime, a more elaborate aerodynamic theory will show that the aerodynamic damping itself can become negative. So the aerodynamic damping, the negative aerodynamic damping itself can produce flutter. And some of you are turbomachinery enthusiasts. Typically, turbomachinery people historically have only looked at that kind of flutter. We could have a whole discussion on why that's so, but usually in turbomachinery, most of the flutter that occurs is a loss of aerodynamic damping, negative aerodynamic damping. In fixed wings, that's not true. Well, it is and it isn't. Theoretically, and even during the design phase, there's another kind of flutter that can occur, which we will talk about. But if it's a competent group of aeroelasticians, hardly ever does that kind of flutter occur in practice, because the people are so good and the theory is good enough that they make sure that doesn't happen. So often when you have flutter in practice, you tell me this, right? With an airplane, it's usually on the tail horizontal control surface, possibly the vertical surface, and it's often due to negative aerodynamic damping. Why? Because the theory isn't as good in predicting. The aerodynamic theory isn't as good at predicting aerodynamic damping as it is in predicting aerodynamic stiffness. So the theory is much more reliable in predicting this kind of term rather than this kind of term. Actually, for piston theory, this is usually pretty good. If you're in the Mach number range where piston theory is supposed to work. Okay. Now, there is the possibility, having said that, there is the possibility of another kind of instability, not flutter, but another kind of instability we talked about earlier in this course, due to this term. Look at this term and this term. Forget about, let's forget about the damping for the moment, right? Look at these two terms. If this term is negative, it can cancel out that term. And when that happens, the total coefficient, which doesn't depend on frequency, is negative. And what kind of an instability would that be, he asked? Divergence. It's a loss of stiffness. You can have negative damping. You can also have negative stiffness due to the aerodynamics. I mean, that's really what divergence is all about. It's all about the aerodynamics creating a negative stiffness, which offsets the positive stiffness from the structure, and then you have the static instability. And of course, there's the static instability frequency is 0, right? And so if the frequency is 0, those terms go away. And right at the divergence condition, how big is the transfer function? When these two terms cancel, how big is the transfer function?
Very big.
Yeah, right. It's big, right? It's real big. It just has to have a huge response. Well, the point is, if you do a gust analysis and you do it carefully, and you really are going to encounter divergence or even flutter, the transfer function will go to infinity at that condition. So, and the response, therefore, will go to infinity, and you'll see it, right? So if you plot gust response versus Mach number versus low velocity versus something like that, as you approach the flutter or the divergence condition, the response will get bigger and bigger and bigger. And so you could do a gust analysis and predict flutter as well, although people normally don't do it that way. We'll tell you how they normally do it. But it's buried in the gust response analysis if you pay attention. Okay, so what do we conclude from this? Remember, this is a one mode model. So what I've said is, in one mode, the only thing that can happen is you can have negative aerodynamic damping, which is not true of piston theory, but it's true of some other aerodynamic theories. Or you could have a loss of stiffness, which means you could predict divergence with this model. Now, you might want to have more modes to get a more accurate answer, right? But the point is, qualitatively, and usually not too bad quantitatively, one mode analysis is okay for negative aerodynamic damping induced flutter. And often when people do turbomachinery flutter, they look at one mode at a time. They don't account for the fact that they may interact. Or you can produce, at least qualitatively, a divergence. But for flutter that's not due to loss of aerodynamic damping and there is such flutter, the point of this homily is that you need more than one mode. You need at least two. So you will see in the literature a discussion of two-mode flutter, or more commonly it will be called bending torsion flutter, because the classical two modes that people look at in an airplane wing are bending, right, and twisting of a wing. You know? And even for panels, which are a different story, plate-like structures, usually you can identify two critical modes. Again, you might need 8 modes if you really want to know the answer to 3 significant figures. I'm not sure why you want that, but you know, if you're doing a thesis, maybe you want that. But probably not if you're working for Boeing. If you get within 1%, that's probably a good day. Because the theory isn't better than that, right? I mean, the theory is probably only accurate to 1 thing. Depends on where you are. At high Mach numbers, you probably would expect to get an answer compared to experiment or flight test within 10 or 20%. In the transect regime, if you got that close, you would think you were very lucky. Very lucky. Okay, so now we need to do two-mode flutter, right? So are you ready to do two-mode flutter? Well, what long as we're in for 2, let's do any number, right? I mean, what the heck? Because we're not, at least I'm not going to do it in detailed algebra. But Daniel Evans has graciously agreed to produce some modes so you can do a real flutter analysis using real modes. But let me tell you what you're going to do. Let's see. Yeah, that's 2. So I'm on 2 here. So what did we start with long ago? If Dan is kind enough to give us the natural modes, which he assures me he's willing to do, then the equation of motion for the nth mode is this, right? Remember what all these are? Do I have to remind you? No. Okay. So you remember what all these symbols are, is that right? Okay, fantastic. But since we're doing flutter, you don't really need to include the gust. I mean, if you've got flutter, the response is going to be huge, and who cares what the gust is, right? And so, and in practical terms, it just makes the computation a little more elaborate and unnecessarily so. So normally in flutter, we only use the generalized forces due to the motion. And what was that? Well, I can probably reproduce it. First of all, it's the pressure, integral of the pressure times the nth mode, dx dy. And according to piston theory, the pressure is minus, this is the perturbation pressure, right? It's really the pressure difference from the mean pressure, right? Minus rho infinity, A infinity, dw dt plus u infinity, dw dx, where again, w is being, or will be expressed in modal form. It's the sum over all the modes of q sub n, psi sub n. However, since I've used the subscript m to denote which mode I'm looking at in the structural equation, to avoid confusion on my part at least, you probably want to use a different subscript here. So I can distinguish between the modes which appear in the expression for aerodynamic pressure and the mode associated with each of the structural modes, right? So we do that. If I use 29 in here and use this in there, then I'll get the expression for the nth generalized force. It will be equal to rho infinity, A infinity, which are constants which come outside. And now I'll have a sum. Well, I can do this too. I have a sum over all the modes, n. And then I'll have, I'll have an integral. And I'll have qn dot psi sub n, that's from this term, plus u infinity qn d psi sub n dx, that's from this term, and all gets multiplied by psi sub m because of that, and then dx dy. Okay? So the point is that in the nth mode generalized force, there are a lot of terms. They're all in whatever the total number of modes I have. All of those modes contribute to the aerodynamic pressure, and of course the aerodynamic pressure contributes to every generalized force for each of the structural equations of motion. Right? Okay. So those are the equations. What do I do with them? Well, how do I do a flutter analysis? Well, I take q sub n or q sub m. They're all the same. And I assume it's q sub m bar. I could either choose e I omega t, or I could choose e to the lambda t. It doesn't matter because, yeah.
The equation 28, there's a minus sign.
There's a minus sign here, right?
Yeah. Just disappear on the equation below the 29.
Which one do you like? Which equation are we talking about? This one?
Yeah, I mean, just this minus sign and.
Yeah, you don't like that minus sign?
I mean,
oh, you want that? I'm sorry. Thank you. I'm sorry. You were complaining about the fact that I dropped it. Well, I just did that to seek repent. Oh, thank you. I forgot. I didn't mean to do that. That's important. Yeah, it's important because if I didn't have the minus sign, I would have the wrong sign for the aerodynamic damping term, right? The other term I could justify because what happens if I blow the air the other way? well, it changes the sign to U infinity, right? So you can also do forward and backward flow if you want to, if you're careful. Anyway, yeah, thank you very much. Okay, so we're going to assume, you want to assume now either lambda t or I omega, it doesn't matter, I'm easy. You want I omega. But now, in general, omega can be a complex number, right? So in general, omega can have a real part and an imaginary part. So if I assume this form of solution, which part of omega governs the instability, whether I'm stable or not? It's really the imaginary part, right? Because this I and that I, all right? So the real part of the exponential is the imaginary part of omega. Either way, okay. Okay, so we're going to do that. We're going to set that into here, and let's see, what do we get? We're going to get m sub m. We have minus omega squared. I really would have preferred to use lambda, but you told me you wanted omega, so we're going to do omega. Plus 2 zeta m, omega m, I omega, plus omega m squared, qm bar, equals summation, well, it's now minus rho infinity, a infinity, summation over n, double integral, I omega, q n bar, plus u infinity, q n bar, let's see, the psi sub n, dx, psi sub m, dx, dy. Right? And I've canceled out the I omega t. Okay. Now I can continue on with this notation, but it's much easier at this point to write this in matrix form, right? So we're all happy to write this in matrix form, I hope. Are we ready to do that? Okay. So if we write this, this is, yeah, I'll call this 30. 31, 32, 33 is a magic number, 33. We're going to write 33 in matrix form. So, and we're going to put everything on the left-hand side because everything depends on q sub n bar, right? This is now a set of linear algebraic equations to q n bar. We're going to seek the non-trivial solutions. So we want to write this in terms of some matrix multiplying the column vector of all the q sub n's, right? And we want to set that determinant of the matrix equal to 0, because that will be non-trivial solutions. And when we set the determinant to 0, it will be a function of this frequency, which we don't yet know. This is not like the Gus case. We don't know the frequency yet. In fact, that's really what we're seeking, right? Because we want to know whether the frequency has an imaginary part which is positive or negative. That's going to tell us whether the system is stable or not. So we're going to set the determinant to 0, and it's going to be a function of frequency. In this particular case, what kind of a function of frequency will it be when I set that determinant to 0? Well, let's go ahead and maybe it'll become clear. First of all, we're going to write this in matrix form. So we're going to write this as some matrix times all these qn bars equals, of course, a column of zeros, right? That's what we want to do. And all we want to know is what that matrix looks like. I mean, that's the first thing we want to know. So let's figure that out. I claim that there's one, I'm going to decompose this into a structural matrix and an aerodynamic matrix, right? Because that's the natural way it happens. The structure group gives you the structural matrix, the aerodynamic group gives you the aerodynamic matrix, and you have fun. So the structural matrix is just going to be diagonals because we have used eigenmodes which have uncoupled all the structural terms. So it's going to be m sub n, that's the times what? Minus omega squared. Is this, well, let's do it this way. Yeah. Times another diagonal, which is going to be minus omega squared plus 2 zeta n omega n I omega plus omega n squared. Right? So that's the structural matrix. Right? I mean, you could also put these terms multiplied by these terms. It's the same thing, right? They're just two diagonal matrices. So this is the structural matrix. What does the aerodynamic matrix look like? Well, it's full. It's not. We haven't uncoupled the aerodynamic matrix, right? In fact, that's difficult to do, and rarely done, if ever. But you could. I mean, you could, but usually people don't do it. It will look like this. You will have, first of all, you have a rho infinity. You have an A infinity. That minus sign, which I left out, but should have been included. Remember, I'm moving all these terms to the left-hand side, so that minus sign gets changed to a plus sign. And then I have terms, a typical term in this matrix looks like the following. It's I omega, the double integral of psi sub n times psi sub m dx dy. Yeah, hold on, sorry, thank you. Plus u infinity double integral of psi sub n respect to x psi sub m dx dy. I mean, these are just numbers, right? But they depend on two different subscripts. So this is a full matrix. It's not true that this is 0 unless n equals n. So each element in this matrix is governed by that. Okay. So now if I write this symbolically, structural matrix plus aerodynamic matrix times the Q's, then I want to set that determinant, the sum of those two. Thank you. The sum of those two matrices is 0. And when you're doing this for the first time in detail in the quiet of your room, you might want to just do 2 modes first to see how it works, right? Also, the advantage of doing 2 modes is, well, I'll tell you the advantage in a moment. Okay. So now, knowing what this form takes, when I set the determinant to 0, what kind of an equation will that give me to determine the omegas? Well, what?
Eigenvalue problem.
Well, it's an eigenvalue problem, but it's a special kind of eigenvalue problem, because normally eigenvalue only appears in one form, like omega squared or omega or something, right? Here I have omega squared, and I also have omega, right? So it's an eigenvalue problem. So I can't solve it in the usual way, because the standard software doesn't handle this. But I could do one of a couple of things. First of all, you could, this is a second order equation, right? Because of the omega squared terms. I could introduce a new variable and write this all in first order form, in which case it would become a standard eigenvalue problem, except it would be non-self-adjoint. And so you couldn't use the usual software that does only self-adjoint systems. You'd have to use a more specialized eigenvalue solver. Or you can multiply out this determinant and get all the terms, and this is what I was looking for, all the terms in its great glory. What kind of an equation in terms of omega would that be? As opposed to transcendental, would be one, it's not transcendental. What other kind of equation could it be? That's a polynomial. That's what I was looking for. It'll be a polynomial omega, right? And so I just need to find the roots of that polynomial. except it's a polynomial with complex coefficients because you insist on dealing with I omega. But I can easily get around that by going back and replacing I omega by lambda, and then I would have a polynomial with real coefficients, which I would like better, you see. But even you can't get away with it entirely. That's fine, but that polynomial with real coefficients will still have complex roots, right? Lambda will have a real and imaginary part, just as omega will have a real and imaginary part. But if you do either the lambda t, then you're looking for the sign change of the real part of lambda, right? That tells me whether I'm stable or unstable. So particularly for the two-mode model, that would be easy to write out, fairly easy to write out. I'm not sure you'd want to do it for 5 modes. I mean, you could, but I'm not sure you want to. By the way, even for 2 modes, what will be the order of the polynomial? What will be the degree of the polynomial? Can you imagine from looking at how this appears? If I have 2 modes, well, if I have 1 mode, it's going to be a quadratic, right? In omega. If I have 2 modes, what do you think it's going to be? 40. If I have 3 modes, it's going to be 6th degree and so forth, right? So even for 2 modes, you're going to have a quartic equation which does not have an analytical solution. So you'll have to use some numerical procedure to find the answer. Yeah. But you can do that. Now, what people actually do in practice is a variety of things. And so let me tell you what they do in practice, unless there are questions about this. This is what I'm going to tell you about the homework. I'm going to assign a homework problem, which is to take the mode shapes that you're going to be given and the generalized masses and the natural frequencies and using piston theory and aerodynamics and do a flutter analysis. Okay. I think you will be able to find a piece of software in MATLAB which, if you assume the form e to the lambda t, will take a polynomial or take that form. I think they'll construct the polynomial for you in MATLAB. I don't think you have to do that, and find the roots of that system. So that's the good news. That's the good news. But let me tell you what flutter engineers do sometimes, rather than finding the roots of the polynomial. So let's see. Assume. So alternate ways to do flutter analysis. Assume Q sub n equals Qn bar e to the lambda t, and use MATLAB to find possible lambda. And you'll want what? You want to plot lambda versus some parameter like u infinity, right? For a given altitude, you can pick sea level if you like. That'll give you rho sub infinity, a sub infinity, and then you can vary u infinity and see how fast this structure has to fly before it flutters. Okay, you can do that. Okay, all right. So that's alternate one. There's some other possibilities. What other ways could you do it? Well, rather than doing this, you could have time marched, right? You could go back to you can use MATLAB for that too, right? You go back, you have the set of original differential equations before you assume this, right? You could set some initial conditions, let it march in time for a given u infinity, and see if the solution grows or decays. That's not what flutter engineers normally do, but in this case, that would be possible. And you might even want to do that just to check that the two methods give you the same answer. Okay? Okay. What else might you want to do? What other ways? Well, I'm going to tell you the bad news. If you're not using piston theory, for something other than piston theory. The A matrix, that's the aerodynamic matrix, right? The aerodynamic matrix is only known numerically as a function of frequency, omega, only known numerically. I don't have an analytical form, right? And usually only known for real, not complex, values of omega. That presents a challenge. You remember? What I said was, yeah, we'll construct this wonderful matrix. It'll be a polynomial omega or a lambda, and we'll find the roots. Well, usually the aerodynamic matrix, we don't know the elements of that matrix, except numerically. That is, the aerodynamicists will say, you give me a real value of frequency, and I'll tell you what the aerodynamic matrix looks like. And you say, well, thank you very much, but that's not what I was hoping to get. Well, that's all I can give you. And be happy. Okay, go ahead.
Piston theory, is that what we've been using? Or which aspect of this?
Oh, no, piston theory, you have an analytical form, right? That's why I introduced it, because everything is much easier with piston theory, which is one more reason it's loved by aeroelasticists.
So I don't remember if it's sociable. What is piston theory?
Well, piston theory is this phrase says that this is minus rho infinity. I'm sorry, I thought I said that.
I just remember you mentioning it, but I don't remember.
Yeah, this is called piston theory, and it's just a name, right? You could call it green apples, but the rest of the world calls it piston theory. And there are reasons for that. And it's a theory that's useful for Mach numbers, supersonic Mach numbers above 2. Yeah, and it was late coming to the aeroelasticity game because people didn't fly supersonically for a long time, right? And the initial theories, and the ones we'll discuss at the end of the course, are actually much more elaborate than piston theory. But you're not ready for that. At least I'm not ready to discuss that yet. So what I'm saying is, even in the simple, let me point out another thing. I'm getting ahead of the game there. Even in the incompressible flow, which was a theory that was worked out by a fellow named Theodorson, it turns out that the aerodynamic matrix has elements which involve the frequency, and for certain cases you can work them out analytically, except the frequency appears as the argument of a Hankel function, if you know what a Hankel function is. Hankel function is a cousin to a Bessel function. So the point is you've got these very elaborate functions which embedded in them have the dependence on frequency. And therefore, it's not going to be a polynomial on frequency when you multiply the matrix out. But even when you go to compressible flow and transect flow, you don't even have it in terms of well-defined functions like Hankel functions. All you have are numerical values that come out of a computer code based on a certain numerical solution technique. So then the question is, yeah, we got time to discuss this. The question is, if I have an aerodynamic matrix which whose dependence is only known numerically as a function of frequency, you tell me it's 5 hertz and I'll give you the elements of that matrix. What do I do then in terms of predicting flutter? Because I can't just try to find the roots of a polynomial. Well, there's one saving grace, and that is at flutter, if I could ever find the condition, the frequency is real in at least one eigenvalue, right? There's one root whose imaginary part of the frequency has gone to 0 at the flutter condition. Okay. So how might I try to chase that in some way? Any suggestions? What people in the modern era, I don't know what you're using at your company, but in the modern era, people by and large are using something called the Pique Method, which in terms of our notation, you might call the Lambda Omega method. Okay? So let me briefly describe that. I have the structural matrix. I have the aerodynamic matrix. I'm going to set the determinant equal to 0, right? Or another way to write it would be, I could, recalling what the structural matrix looks like, it's M, the mass matrix, and I'm going to deliberately write it this way, recalling that lambda and I omega have a correspondence. It's M sub M times lambda squared, where this is a diagonal matrix, and then it's plus M sub M times a diagonal matrix of natural frequencies. Note, I have very carefully set the structural damping term to 0 for simplicity of this conversation. And then I have the aerodynamic matrix, which depends on frequency, where, again, lambda and I omega are related by that, by definition, right? And then if I want to, I can take all of that and multiply it by G. Okay? So that's the setup. That's the setup. Now, it took someone about 50 years to figure out this is a good thing to do. I'm not sure. Because people are doing it another way, which I won't bother to describe for many years. A fellow named Herman Hossig, who worked for, I think, for Lockheed. Herman said, look, if only I knew those values at the correct frequency, then this is just it's a complex matrix, but it's in standard form, right? And I could think of lambda as being my eigenvalue, and I could try to, for some initial guess of A, I could compute lambda, right, using standard eigenvalue techniques, right? So he said, let's guess omega. Remember, he's trying to find the flutter condition, so it's going to be a real number, usually. Guess omega and determine lambda in the usual way. And if you want to, you can again think of this as multiplying this out and you get a polynomial in lambda for a given guess on omega, right? So lambda will turn out to be something. It will have a real part and an imaginary part. And if we made a really good guess, by the way, we had to pick a flow velocity too, right? Because when we're making this guess, we have to guess the flutter frequency omega. Also, since we're seeking this flutter solution, we'll guess a velocity. If we made a perfect guess, it would turn out that lambda I would be equal to the omega we guessed, and lambda R would be exactly 0. What are the chances of that happening? Slim and none, as we say. Not likely. On the other hand, if you've been doing this for a few years, you can say, last time we built an airplane like that, and now I know what the natural frequencies are. I bet the two modes I think are going to couple are the mode at 5 hertz and 15 hertz. I bet the flutter frequency is going to be 12. And by the way, this plane is a little more flexible than the last one, which fluttered at 700 feet per second. So I think this one will do 600. Okay, it's not like you are totally clueless as to what a good guess would be. So you put those in, and you get the lambdas, and they're not the same, right? But you get a frequency, and of course you get a real part too. what you do is you take this lambda I and use that as your new guess for omega. And then you keep iterating, and most of the time you get where you want to go. Okay. You can actually play this game at any flow velocity, not just the flutter velocity, except that any other flow velocity, the lambda R will never be 0, right? And then you can sort of interpret. It's not really a. Remember, the assumption about the aerodynamic matrix is the omega is purely omega, right? The lambda real is 0. So when you do it at an off-flutter condition, you get an answer, but how much physical credibility you give that answer may be questionable. Anyway, this method, in the standard terminology that appears in the literature, lambda is usually called P, so you assume a solution in the form either PT. And omega in the aerodynamic theory doesn't really appear just as omega. It's always omega times some characteristic length like the chord divided by the flow velocity, which is defined to be K, a reduced frequency. And so people call this the PK method because of that. And that's what people mostly do today. Is that what you do?
You do G method?
Oh, you still use the G method?
Not the VG, the G
No,
method.
yeah.
G is like when you assume that damping is analytical function.
Yeah. You still use the VG method.
We both just VG, but G it's modified picking.
Okay, modified PK. Okay, fine. Yeah. So the thought I want to leave you with is that because of the way the aerodynamic theory is usually available to you, or the results of aerodynamic theory are usually available to you, it's only available to you for real values of frequency. And so you can't do what you would like to do. So you're forced to a somewhat convoluted but effective way of finding the fun point. But the good news is, for piston theory and for your homework, you can do what you might be normally hoping to do. Namely, you just assume a form of the solution, either E of the I omega t or E of the lambda t, and then appeal to MATLAB, and away you go. So you should be okay on that. I think that's all I want to share with you. See, the homework is due today, right? The present homework is due today. Let's see, we're going to have midterm break next week. Is that true?
Yeah.
Next week. So the next homework, which will be due to do this flutter analysis, will be due the week after that, because this will take you a little bit of time, right? And you're going to produce all these wonderful things that they need, right? Yeah. And we'll send that to you. Now, for those of you in Stockholm, I think Thursday will be your last class. So what I plan to do on Thursday is I plan to start talking about unstereodynamics. And I'm going to start in the middle of the discussion. Actually, what I'm going to do in one lecture, I'm going to summarize everything you need to know about unstereodynamics, but at a fairly high level, right? So those of you in Stockholm will get that. It'll be an introduction to the subject for you. And all of you, I hope, will start reading chapter 4, where the full gory details of classical unstereodynamics are given. And Stockholm, I would not want to deny you the privilege of doing this last homework. And so this is going to be your final project for your half of the course. So we're going to let you do the flutter analysis too. I know you're thrilled by that, right?
Yeah.
Yes, we are.
Yeah. It's always good to have eager and enthusiastic students. So thank you for agreeing to do that. And again, you're welcome to participate in the rest of the course as well. We will not charge you anything extra if you do, or you can simply look at the lectures at your leisure online and see if you would like to do it that way. Any questions here in Durham, North Carolina for the day before we wind up? Any questions? You all know what you're going to do for the homework? No. Well, you will discover it as you think more about it. Stockholm, any questions before we conclude for the day?
Yes, about the previous homework.
Yes.
I could not understand the meaning of cross correlation. When we have a tau in cross correlation and we set it to 0, that gives us an amplitude square. Let's say for phi alpha alpha, which basically will mean a power amplitude square, which is basically the potential energy. But when you have a phase lag tau, then what does it mean?
Okay, I think I answered your question. Let me see if I did. You're talking about the cross correlation, is that right?
Yes.
Okay. So let's look at a cross correlation. And just to be definite, we'll look at the cross correlation between alpha and alpha naught. In general, it will be a function of some time delay tau. And it's defined to be, what? 1 over t minus t over 2 plus t over 2 alpha t, alpha of t times alpha naught of t plus tau, dt. And your question is, what happens if I set tau equal to 0? Is that right?
My question is, what is the physical meaning when we set tau equal to 0 and when we have tau non-zero?
Yeah, that's what I thought. Yeah. In this case, that's interesting. I never really thought about it before because usually people are not interested in this function for tau equals 0. But let's, what it is that's a good question. I think you have asked a different question, which I've never heard before. Then it is this, clearly. It's alpha t times alpha naught t. That's what it is, but so what? It's not the mean square of alpha. It's not the mean square of alpha naught. It's the mean square of alpha times alpha naught, and, for whatever it's worth. I wouldn't give it any great physical significance. I mean, what normally happens is people look at what happens when tau is very large. If you look at this cross correlation function and let tau become very large, if that cross correlation function goes to 0, that tells you that alpha and alpha naught are uncorrelated at large times. I suppose if this turned out to be 0, which it could be, right, even at tau equals 0, then that would tell you it's uncorrelated at short times too, right? Yeah. So what you might do, another thing you might do is you might compare this cross correlation. You could compare it to the autocorrelations, right?
Yeah.
And if this cross correlation is small compared to the autocorrelations, you can say, well, those two quantities, alpha and alpha naught, must not be very well correlated. Now, in the example we're doing, right, we know that alpha naught is driving alpha, so you expect them to be pretty well correlated. But if I just had two random signals and I didn't know much about them, and I want to know, are they related in some way? Is one causing the other, right? You can imagine having some experimental data. Then by looking at the cross correlation and comparing it to the size of the autocorrelations, you could get some sense about how important the correlation is between those two signals. Does that help?
Yeah. Thank you.
You're welcome. That's a good question. I'd never thought about that, actually. Yeah. But I don't give any particular significance to the cross correlation when tau equals 0, unlike the autocorrelation, where it's definitely the mean square, and that's often what you're interested in. Any other questions from Stockholm?
No, thank you.
Okay, well, have a good